Hi, good that you're watching this video. It will be your lecture for today. Since unfortunately I'm abroad, so this is the alternative. We're going back to how it was last year, and you have this lecture online. So let's get started. Maybe online is not too bad because actually we're revising subjects. I'm not going to teach them anew. What subjects are we revising? Well, it's algebra, algebraic scales, trigonometric functions, polar coordinates, trigonometric identities, logarithms, and derivatives. Yeah, I hope you all met these subjects before and know something about it. And now I'm mostly going to tell you what exactly you were supposed to know for the rest of this course. Well, let's start with the first one with a little historic view. Algebra, where does that word come from? It's a very old discipline, and actually it started, the basis of it can be found in a book from 830, the year 830. This book, it's from the Middle East. It's called well, in Arabic, not my first language, Al-Kitab al-Muqtasar fi Hisab al-Yabar wal-Muqataba or something. But what's interesting is that word al-Yabar, which is actually where the name algebra comes from. So they took somehow the word in the middle of this book title, and that developed into our word for algebra. So what does it actually mean? It means the compendious book on calculation by completion and balancing. This book is really the first book where they compute things by replacing numbers by letters and manipulate expressions with those letters. So that's quite special. But let's get going ourselves. So I'm not going to give you a real course on algebra right now. We're actually just going to do some sort of warming up. I'm going to ask you to do these 4 tasks, and then you can do that while you pause the video. And then when you start the video, you'll find me again, and I'll show you how this sort of task is done. And that will be our revision of algebra for today. So good luck, and see you in a little bit. Now, this should have all been roughly familiar, but maybe you got stuck on some details. So let's have a look. Here I want to free the x and get an expression in y on the other side. So first step is to get rid of the fraction, and I do this by multiplying by the denominator. So I multiply both sides by the term in the denominator, and what I get is y times 5x minus 2 equals the denominator here, 2x plus 5. So I want to bring everything with an x to one side and all terms without x to the other side. So that means I have to get rid of the brackets here. So that's the next step. It will be 5xy minus 2y equals minus 2x plus 5. And then we can do what I plan to do, get everything with an x to one side. So that means we get 5xy plus 2x equals, and everything without an x to the other side. So I take minus 2y to the other side, 2y plus 5. So all in all, what I've done here is a plus 2x and plus 2y, and in both sides, really. Okay, now I've got all terms with an x here on the left. I can put the x outside the brackets. I get x times 5y plus 2. And here it's still the same, 2y plus 5. And now to free up the x, I divide by this term. So this division by 5 by 2 gives me x equals to 2y plus 5 divided by 5y plus 2. All right, so let's run through it once more. We started with this fraction. We want to get an expression of x into y. So we have to free up the x. The first step is to get rid of the fraction by multiplying with the denominator. The next step was to get rid of the brackets. Then we make sure that we get all terms with x on one side and all terms without on the other side. I bring the x outside of the brackets, and then I divide by this term that I get. That's my answer. Now let's look at exercise, warming up exercise number 2. Here there's some Greek letters. This is the capital lambda. Lambda m is lambda m0 minus kappa or k square root of c. So maybe also challenge here is not to get distracted by all the notations, the subscripts, superscripts, the strange letters. All they really want again is to express c in terms of the rest. So that's what we're going to do. We're going to first take this term to the left and the lambda m to the other side. So that would give me k squared of c is lambda m0 minus lambda m. That's the first step. Nothing too dramatic happens here. Then we divide by the k. We get the square root of c equals the lambda m0 minus lambda m divided by k. And then the very last step is just to simply square both sides. So, well, I might just about fit on my screen. So c is lambda m0 minus lambda m divided by, and then don't forget to put the bracket. So we need that whole fraction squared. So more or less same sort of procedures as there, but with more difficult terminology, by which we did not get distracted, I hope. Let's go to the next one. Totally different. We're supposed to simplify this expression. So now it's about decomposing a quadratic expression x squared minus 2x minus 8. Well, I hope that you remember that if you want to decompose such a term, you first look here, minus 8, that's for example minus 4 times 2. And that's what we want, so we can decompose this as x minus 4 times x plus 2. And then here we find x squared minus 16. That's also some special term that you can always decompose because square minus a square, which can always be decomposed by using the square roots of these things. So that's the famous thing that a squared minus b squared equal to a plus b times a minus b. This is, of course, a super important decomposition. So let's use it here. It's then x minus 4 times x plus 4. Of course, I can also say x plus 4 times x minus 4. It's the same. But I did it this way because now you see that there's a term x minus 4 both in the denominator and the denominator. So they cancel out. And I'm left with x plus 2 divided by x plus 4, which can not be simplified in an obvious way. So we're very happy with that as an ending. And that brings us to the fourth task. And the fourth task is here. And it's a bit the other way around. We want to simplify things by joining them. And let's see. With normal fractions, you do that by creating equal denominators. If I have 1/3 plus or minus 1/7, what I need to do is make sure I get equal denominators. So I will make of this 3 21st plus no 7, of course, 7 21st plus 3 21st, and then add them up. Then same here. Same here. Nothing different. We should just make sure we have equal denominators. So that should be the denominator x plus 1 times x minus 1. So I multiply both sides here by x minus 1. I get x minus 1 divided by x minus 1 times x plus 1. And here I get both sides times x plus 1. So it's 2x times x plus 1 divided by x minus 1 times x plus 1. All right, now they have equal denominators, we can join them. So you get x minus 1 minus, between brackets, 2x times x plus 1 and divided by, I could actually get rid of these brackets here. It will give me x squared minus 1. I could simplify the denominator a little bit. Take the opportunity to do that. So first get rid of the brackets here. So I get x minus 1 minus 2x squared minus 2x divided by x squared minus 1. And that is minus 2x squared minus x minus 1 divided by x squared minus 1. Phew. So that was our warming up. I hope you could follow this and it sort of refreshed your mind. If you still have questions about this, just leave them in the forum so that I could come back to it or ask your other students. I think altogether you should be able to definitely reproduce whatever is necessary to understand what just happened. All right, great. Let's move on. Learning about trigonometric functions is always a bit confusing. And the reason is that when you first encounter them, you learn about trigonometric functions in triangles and triangles only, as if you can't compute the sine of a quadrilateral angle. And another thing that's confusing is that later then the sine becomes just a button on your calculator, whereas what it really is a sine, a cosine, the proper definition is geometric and has to do with a circle, a unit circle. And I want to remember with you what that was again. So here you have this unit circle. It has a radius 1. And I place it in a coordinate system so that the middle of the circle is at the origin. And then I can look at the radius that has a positive has an angle with a positive x-axis of t. Well, then this radius will intersect the unit circle at the point t. And by definition, the coordinates of that point are cosine of t and sine of t. So what you can really easily see, if t is 90 degrees, then the cosine will be 0 and the sine will be 1. But of course, we want to be able to compute it also for different angles, but I'll get to that. But first, I want to point out that there's also a nice geometric meaning of the tangent here. If you add two vertical lines, that x is minus 1 and x is 1, and then you find another intersection point of this radius there, and by definition, the coordinates of this point are minus 1, tangent of t, or if you happen to intersect the other line, then it will be 1, the tangent of t. So the y coordinate there is then the tangent of t. So that's excellent. We have a geometric interpretation of all these trigonometric functions. And there are, of course, more trigonometric functions. You'll find them in Wikipedia. They're also important. But for now, I'll stick to these. And you know the geometric interpretation, so that's good. Well, I'm sure you've encountered this type of tables with exact values of the sine, the cosine, the tangent for specific angles, either in radians here or in degrees. And well, you can learn them by heart if you like that. But personally, I hate that. So I'd rather have a clever way to compute them. And you've probably seen that before as well. There are two very famous triangles. Here they are. And one of them is actually half of a square. And the other is half of a rectangle, of a regular triangle. And you see, well, half the square means that two angles are 45 degrees and one is a right angle. And then the edges are 1, 1, square root of 2. And yet the half triangle, half regular triangle, equilateral triangle, the edges are 2, 1, and square root of 3. Check the Pythagorean theorem really holds. So the angles there are 30 degrees, 60 degrees, and 90 degrees. And yeah, we can use, if we just remember these two triangles, then we can do all these special values for the cosine, sine, and tangent. just by using this and the unit circle. So that's the next thing I would like to show you. And then after that, I will also show you how you can use the unit circle to see some identities that hold for the sine and the cosine. All right, here we go. Okay, so let's go for it. Let's compute the sine of pi over 3 using our special triangles and the unit circle. So the first thing I'll do is I'll sketch this angle as a radius in my unit circle. So it should be more or less over here. And here's my angle pi over 3. Now let's try and squeeze that special triangle in here. It's going to be a bit small, I'm sorry. Well, there it is. But we're in a unit circle, so the diagonal here, this side is only 1, whereas in our special triangle it's 2. So to really recognize our special triangle here, we have to you have to shrink it with a factor half, which means these sides are not the square root of 3, but half the square root of 3. And this side is not 1, but simply 1/2. But hey, all the work has already been done now, because the sine of pi over 3 is simply the y coordinate, which is here. We go up half square root of 3. So that's my answer here, half square root of 3. And also the cosine is that. So the cosine of pi over 3 must be 1/2. So let's try the same trick again, but now slightly different. The cosine of 5 over 4 times pi. Well, that's more than pi, so we're more than a straight angle away from the positive x-axis, and then here another 1/4. So I'm really interested in what's happening here. And what's left after I've done already this pi is a pi over 4 angle here. And then, of course, the total angle is 5 over 4 pi. And now I draw my special triangle because I recognize the angle, and it's here. But I have the same problem because, again, this one I know has length 1, and whereas here it's the square root of 2. So again, I need to shrink it so it fits in. I have to multiply by a factor of 1 over the square root of 2. So that gives me here 1 over the square root of 2. And there 1 over the square. I'm sorry if you can't read. You can hear me, right? So there you go. The cosine is, the cosine, we're on the minus side. So it must be minus 1 over the square root of 2. And then, of course, we can't leave a square root in the nominator. I hope you've been brought up well and you know this. So I multiply numerator and denominator by the square root of 2, and I get square root of 2 over 2 minus, so that is minus 1/2 square root of 2. Great. So these are some sample calculations. I'm sure you can do similar things now for similar angles. And this is for if you don't want to memorize big tables. Now let's look at some more generalities that we can understand using the unit circle. For example, this equality, the cosine of theta is the cosine of minus theta. Well, I've used the theta just to show you that it doesn't always have to be a t, like Greek letters as well, for angles. And why is this true? Well, let's draw some radius under some angle theta here. Then minus theta would be going around clockwise. So, but just as far, so we would end up going about over here, minus theta. And, you know, if you follow me, of course, these two are a mirror image in the x-axis. And that means that they must have exactly the same x-coordinate here. My drawing is not brilliant, but you get the point. This is exactly the cosine of theta, whereas this is the cosine of minus theta, and you know, they are both the same x-coordinate. So that's why this equality holds. Now this one is slightly more difficult. Let's look at an example. Theta, the cosine of theta, let's take a small theta here. Theta, the cosine is of course over here. Here's the cosine. And now why is that equal to the sine of half pi minus theta. Well, where's half pi? That's of course, that's over here, that's straight, and then we go theta away from it. Here, we go up like here, and this is half pi minus theta. And if you take the average of these two angles, you get half pi minus theta plus theta is half pi divided by 2, because it's the average, 1/4 of pi. So these two lines are really just each other's mirror image in the line here under an angle theta is 1/4 of pi. Oh, that's the line y is x. And what do you get if you take the mirror images in the line y is x? So that means that for coordinates, you exchange the y and the x coordinates. So that's why the cosine of the one is the sine of the other, because this is just taking mirror images in the line theta is 1/4 pi, or another description is the line y is x. All right, so this is just some background about how these identities that you should know can also be easily, or relatively easily derived from the unit circle, our big friend, the unit circle, and our other friends, the famous triangles. All right. So in the beginning, really, there was only a plane with points and circles on it. And the old Greeks, they didn't even use coordinates. Only much later, Descartes introduced the idea that you would draw these two sorts of axes on it, x-axis and y-axis, and then give coordinates, x and y, to each point on the plane. And of course, this has been very, very fruitful and very important. But really, Descartes' way of putting those coordinates there is not the only way. There's Cartesian coordinates can also, can be not used, and instead you could use polar coordinates. And it really depends on the situation that you're describing. What's best? Polar coordinates doesn't have an x and a y axis, but it sort of turns it into a coordinate system with circles and radiuses, radii. Right? So the r then gives you the distance to the origin. Those are the circles for fixed distances. And the theta gives you the angle to the positive x-axis, of the positive axis. There's no x-axis now, really. All right, so these are coordinates that describes points just as well, but just differently. And you have to be able, unfortunately, to move back and forth between these two ways of describing points in the plane. So let's have a look at that. So let's look at a little example. Here you have a point which is described by Cartesian coordinates -3, 3. Now, what are the polar coordinates? We have to know the distance here. Well, you can compute it. And we have to know the angle. Well, the distance turns out to be 3 square root of 2. And the angle turns out to be 3/4 of pi. So that means the following. It means that the polar coordinates are 3 times square root of 2, comma 3/4 of pi times pi. So how could you compute this? I like to see it geometrically. Here's our famous triangle again, the 1, 1 square root of 2 triangle, but now it's 3 times as big. So of course the diagonal is then going to be 3 times square root of 2. In the bottom corner we have 1/4 of pi plus the half pi that we have in the first quadrant gives us 3/4 of pi. But no one's going to stop you to use the general formulas, which is actually the bottom two here. But the first one is for r. R is the square root of x squared plus y squared. So that's simply Pythagorean theorem. If you use it here, you get 3 squared plus minus 3 squared is actually 18. So the square root of 18, and it can be simplified to this 3 times the square root of 2. And then the other one gives you a formula actually for the tangent of theta. So you have to watch out a little bit. You get the tangent of theta is the y, that's 3 divided by the x minus 3. So we get -1 And actually, if the tangent of theta is -1, you can still have two thetas, namely either 3/4 of pi, which is the correct answer, or 7/4 of pi. Yeah, just opposite this. Because if I have the point 3, -3, and I do this division, it's also -1. So you get an opposite point has the same tangent. So you have to think a little bit to make sure you pick out the right theta in the end. You know, check out where are your Cartesian coordinates and make sure you choose the right one of the two angles. Okay, you can do it. Also, we could check the formulas for the other way round. The other way round is sort of, you know, it reminds you of the cosine and the sine as coordinates of the unit circle. If you make the circle r times bigger, then of course the coordinates are going to be r times the cosine of theta and r times the sine of theta. So that's what this comes from. So you could check for yourself that 3 times squared of 2 times this cosine of 3/4 of pi is 3 times the square root of 2 times a half square root of 2, and then you compute and you get exactly your -3. And same for the sign. I think I forgot the minus sign there, but you know what I mean. All right, so that's how you can move back and forth. Either, what I would prefer, make a drawing and use a bit of your insight, or use these lovely formulas. So as a little test for yourself, try to compute the polar coordinates of this point over here with Cartesian coordinates 2, -2 square root of 3. So pause the video for a moment. Yes, I hope you were successful. The answer is this. So you can, again, use a special triangle and fit it in, because it does fit in. It's actually twice this half of an equilateral triangle, twice that size. So you can fit it in, and then you find r is 4, the distance to the origin is 4. And you can squeeze this little, well, you have the angle that is not red, it must be 1/3 of pi. So the red angle must be 1/2 of pi. The other way would be to actually fill in the formulas, and I'm sure you were successful with that. All right, let's move on. In this last little example, I want to show just one more thing. If the polar coordinates are 6, pi, that means that we're simply on the x-axis. So the Cartesian coordinates will be -6, 0. It's good to just mention that, of course, the first coordinates is always going to be 0 or positive. If it's 0, means that you're in the origin, and usually you have to watch out a little bit with that for polar coordinates, because then what's your theta? Usually it's bigger than 0, it's positive. And the angle, of course, is going to be between 0 and 2 pi, where they prefer 0 over 2 pi. So just some restrictions there to make sure you get them correct. All right. So this slide is probably going to give you some shivers, because these are the horrible doubling formulas for the trigonometric functions. And yes, you'll have to know them by heart for a test. I promise you there would be some things to learn by heart for the test, and here they are. And especially useful to remember are actually the doubling formulas that follow from them. These are useful later when we do some integrals. But for now, we just have to learn them by themselves. And on the next thing I'll do is actually try to convince you that you actually, if you're really lazy, you just have to remember the one at the top for the sign, and then all the others will follow from it. So that's great. Okay, so let's take the challenge to look at the doubling formulas for the sine and the cosine. And I always find it very difficult to remember them. So let's see how far I get. First, let me start with these identities that, well, one of them we already discussed, and then this one is very, very central. The cosine and the sine are by definition the coordinates of this point on the unit circle. So The fact that they're on the unit circle means that the distance of this point to the origin must be 1. And that's simply what this is expressing. Very important thing about cosine and sine. Squared plus squared is 1. Now the doubling formula. And the one thing you need to remember it all in a sense, is that the sine of x plus y is, and this is the most straightforward thing, is the sine of x times the cosine of y plus the cosine of x times the sine of y. So somehow this is the most simple thing about it. It's just first sine cos and then cos sine with a plus, so there's no sine to remember. So the easiest of them all is the sine of x plus y. And you can use this one together with these things, and maybe one more, the cosine of x is the sine of half pi minus x. You can use this to get all the other equalities. So let's begin with a simple consequence here. If I take x to be y, then the sine of 2x is the sine of x plus x. Now apply these rules, and this will be an x and this will be an x. It's twice the same, so I get 2 times the sine of x times the cosine of x. It's a very familiar formula, hopefully. And well, let's see if we can find the sine of x minus y. Sine of x minus y. That should be not so hard, because everywhere where there's y here, we change it by minus y. We can do that. We get sine of x times cosine of minus y. You sometimes have to brackets. Sometimes I almost forget. It's better to put brackets, then it's always clear. Cosine of x times the sine of minus y. Now, this cosine of y is the same as cosine of minus y. So you just get sine of x cosine of y plus cosine of x. Yeah, and then here you get a minus, because this is the sinus of y with a minus, but of course we're going to put the minus here. So, so there it is. So here's one of the other in the table. And now the more exciting one is to jump to the cosine. So how do we do cosine of x plus y? If all we remember is this one, well, what do? We just say this equals, using this formula, sine of half pi minus x plus y, so that's minus x minus y. All right, there we go. This we could, we could cut it in two. We could say this is the sine of half pi minus x. That's one term, minus y. And then we can use the formula that we just wrote here, and use the, instead of x, we use a half pi minus x. So what I get is the sine of half pi minus x cosine of y minus cosine half pi minus x times the sine of y. Okay, but the sine of half pi minus x is the cosine effect, so it's the cosine of x times the cosine of y minus cosine of half pi minus x is sine of y. Now we use the same one, but with the coordinates reversed, so the sine of x times the sine of y. Great, so now we've got, and now you can do the last one, the cosine of x minus y yourself. I wanted to show you as another one, what do you get then for cosine of 2x. Cosine of 2x you get by, that's this cosine of x plus x like before. So everywhere we find y here, we replace it by an x. And then you get cosine squared x minus sine squared of x. So it's almost like that one, but then with a minus sign. So it's definitely not 1, it's cosine of 2x. That's wonderful. This is one of the doubling formulas, this one and this one. But for the cosine, there are a few more forms, because in this, you could replace this, because this could be rewritten as the cosine squared of x is equal to 1 minus the sine squared of x. Or even if you want, you could also write that sine squared of x is 1 minus the cosine squared. And so what do you get if you use the second one here? That means you replace this by 1 minus sine squared, so that you get 1 minus 2 sine squared of x. Or you could say, hey, I replace the sine squared here by this, and then I get cosine 2 cosine squared of x minus 1. So what do we learn from this? I'm not going to ask you to do these derivations on the test. Of course not. You've got better things to do. I just want to prove to you that you don't have to remember by heart, that you could, in principle, derive them all if you just remember this one. So what we've learned from this is that we had a little challenge to follow all these derivations. That's really good test in manipulating everything we know in the context of equations. So that was a good challenge. We see all these identities together on the blackboard now, and maybe that helps actually to memorize them after all. So these doubling formulas will turn out to be useful when we compute certain integrals, and that's, I think, the main point where you will meet them. These summing formulas are mostly of theoretical importance. And I actually want to promise you that of this formula that we begin with, I'll give you a very nice and easy proof, but you'll have to wait until we have talked about complex numbers. So that will have to wait. All right, let's move on. So before we forget about all molecules and things, or as this course is supposed to prepare you for computing things about molecules, let's go back to a lovely example that's really at the heart of atoms and molecules. And it's simply about the ground state of the hydrogen atom. And what I find fascinating and amazing, and it makes me really excited, the mathematical way to describe it within quantum physics is simply by a power of E, an exponential. This psi, which is it's called the wave function. In polar coordinates, by the way, this r is an r from a polar coordinates, is e to the power minus r. So exponential e is really at the heart of your subject, of the world, you could say, because the world is built of atoms, and particularly many hydrogen atoms. So E is a super important function. It's not just here, it's also in probability theory. It pops up everywhere in mathematics. So E is important, but also its inverse. So let's move on to its inverse. So it's turned evening here, and I still need to finish preparing this course for you. So we'll finish it by, let's say, candlelight. I think you can see enough of me to follow the course, no problem there. And we're talking about the inverse of the exponential function, and you're supposed to know already that that's the famous logarithm. And if you have the exponential function and the ground number is e, then the inverse is called the natural logarithm, and the abbreviation is ln. And what's good to know about functions and their inverse, that they're actually each other's mirror image, the graphs that is, in the line y is x. So you see that here, the bottom function is the function of ln, and the top function, the graph is of ex. And for example, you know that e to the power 0 is 1, and the other way around, ln of 1 is 0. So they are each other's inverse, and you can use that in your computations, for example. So we just talked about how E is at the heart of quantum mechanics, of the description of the hydrogen atom, but also the logarithm has many, many practical applications. And here's one of them that is of some importance to you, I think, from chemistry. It's the pH value. You see the logarithm of base 10. I said round number before, but the proper English is base. So this is logarithm base 10, and you use it in the computation of pH values. So for doing computations with logarithms, a couple of rules are important, and they're here. The first one is the rule for summation. Ln of x plus ln of y is ln of x times y. And then there's one for differences, and there's the power rule. Ln of x to the power n is n times ln x. So this exponential can be moved in front of the ln. And yeah, these rules will help you doing all sorts of computations. And one of them is here on the right. And I would like to give you a few minutes time to try and solve this equation yourself using these rules. And then the next thing will be me giving you, I think, even 2 ways of how to solve it. So good luck, and stop the video for a moment. All right, so let's practice a little bit with computations with the logarithm, the natural logarithm, ln, and the rules that we know for it. So there are many ways to go ahead. I'm going to show you just one. For example, this one. We start with the square root of x minus 1. We write it as a power. It's to the power 1/2. To be sure, I put extra brackets here. Minus ln x minus 1 is 2. Then I can bring the half in front of the ln. That's one of those rules. Half ln x minus 1 minus ln x minus 1 is 2. Hey, I got half of this and a whole of this, and I subtract this here. So it's minus half ln x minus 1 is 2. Great. So times minus 2 maybe. Times minus 2 gives me ln x minus 1 is minus 4. Then, well, I would like to get rid of this ln, so I do both sides to the power e to the power that side. So then here, of course, the ln will vanish. So I get x minus 1 is e to the power minus 4. And that means x is 1 plus e to the power minus 4. That's one way to do it. And I've got a bit of space here maybe to show one other way that some of you may have done. Because, of course, if you see the minus, you might be triggered to do the division rule. So this is equal to ln square root x minus 1 divided by x minus 1, big brackets, is 2. That's fine. And now we can even simplify this, because here squared, here the big to the power 1. So this is equal to ln 1 over the square root of x minus 1 equals 2. So that means I'm just going a totally different way. Again, I want to get rid of the ln, so I do e to the power on both sides. I get 1 over the square root of x minus 1 is e squared. Now the challenge will be to end up with the same result, right? Ooh, exciting. I have to do 1 over blah, blah, blah to get 1 over. 1 over, I want to get rid of it. So then I get 1. I get just the square root of x minus 1. And here I get 1 over e squared, which we know is e to the power minus 2. I hope this is still in the camera. Yeah, you can still read this. Okay, now I square. So I get x minus 1 equals e to the power minus 2 squared. So x is q. I get the same result. 1 plus e to the power minus 4. There you go. 2 for the price of 1. So I don't think I told you this before, but before I started working in the Freudenthal Institute, I was a teacher for a while. And before that, I was actually a researcher in mathematics itself for some time. And well, I was fortunate enough to prove a few new results and new theorems. But of course, the greatest honor is if somebody at some point comes in and names a theorem after you. So that's one thing Pythagoras definitely did well, because everyone knows his theorem. But nobody knows a theorem by the name of Bos, unfortunately. Maybe I don't deserve it. But of course, never give up. And so I've been a bit bold. And when I was preparing this course, I found this lovely rule. And I've been looking all over the internet, and it seems that it's not terribly well known. So I thought, why not give it a shot? It's my rule. I call it the boss rule, and I need you to spread the news and tell everyone about my rule. And maybe then one time it will be accepted by the community and I will have my own little result after all. So there's the rule. And by the way, I challenge you, because actually this rule can of course be derived of the 3 rules that we had before. So if you want to impress yourself or the others and me, of course, you could send me a proof of this lovely rule. Of course, you can also make me very happy if you use it in the exam or in your quizzes. The boss rule, there it is. So the last subject for now is derivatives. And I don't want to immediately define things. I want to know why are they important for you. And I want to give the example of reaction equations. Generally, you have, for example, A molecules of types A, B molecules of type B, and then they do some chemical reaction, and then you end up with P molecules of type P and Q molecules of type Q. That's the general thing. But a simple example is just that you have hydrogen there and iodide, and they form a reaction, and then you have 2 hydrogen iodide molecules. Very simple, but it's actually not instant. It's not that simple. It takes some time. So it's actually better to look, if you want to have a more precise view, on how the concentrations, how they change over time. So now I suddenly see the concentrations of those molecules as a function of time. That's why I put T between brackets behind it. It depends on time. And then suddenly you could sort of consider the speed at which a reaction takes place, the reaction speed. And it's actually proportional to the derivative of that function, the concentration as a function of time, to, of course, the variable then, which is t. So dA dt, but not exactly that, because you compensate for the number of molecules that is involved in each reaction. You divide by that. And since on the left side, these are molecules that are sort of vanishing, so you get a minus. If you take the others into account, you wouldn't have those minus if those are the molecules P and Q, the ones that are added. And then the rule is actually that, of course, there's only one reaction speed, that these derivatives equate in the following way. And this will play a role later in our course. We're going to look at differential equations and use them to solve issues on concentrations during reactions. Very interesting. Let me show you another use of derivatives in a different context of ideal gas. Well, for ideal gas, we have the ideal gas law, which is V is N times R times T divided by P, where, N is the number of molecules and R is a constant, and T is the temperature, V is the volume, and P is the pressure. And now we're going to fix the number of molecules and the temperature. Then V can be seen just as a function of the pressure P. So the volume changes if we change the value of P. So what's the meaning now of the derivatives? Let's do it in steps. First, we could look at
average change of V when P changes. So you get delta V divided by P, and this is called the difference quotient. Gives you an idea of the average change of V when you change P. And then what you do, of course, is you take the limits of taking delta P to P, and then you get the instantaneous change dV divided by dP, or the dV dP of V when P varies. And what does that mean? Well, let's first compute it. Of course, we know how to do this. N and R and T are treated as constant, so it's really just the constant times 1 over P. And the derivative of 1 over P is minus 1 over P squared. So that's fine, we know the derivative. But what does it mean? Well, it gives you, of course, the slope of a tangent line. And if I just look at the point P, V here, the top point up here, then you see it's quite steep, so the derivative there will be high. And what does it mean? It means that if we change P a little bit, starting from this position, say we make it a little bigger, then it's steep but negative, so it will then strongly respond by the volume going down. So it was small increase of the pressure will suddenly lead to a big jump in volume, smaller volume. Whereas if you look at the point more that direction, the other point there it's not so steep. And if I would increase the pressure here with the same small amount, then the response of the volume would be much less drastic. So what you see that actually the bigger the pressure is, the less dramatic the response of the volume is to a small increase of the pressure. So in that sense, the derivative actually really tells us something about the situation. And that's important to realize if you have derivatives which, with like this, not standard variables, like V and P. What does it mean to take the derivative of one of the other? Well, here you have a good example, and keep it in mind if you meet similar situations. Now, of course, mathematics wouldn't be any fun if you wouldn't get the opportunity to do lots of computations. So at school, if I'm correct, you've learned a whole bunch of rules. And here they are just to remind you, multiple of a function. If a is just a number, then the derivative of 2 times a function is 2 times the derivative of that function. There's the sum rule, the derivative of a sum of 2 is the sum of the derivatives. Same is not true for a product rule, right? Because look, exactly, this is not just the product of the 2 functions, but it's u times the derivative of the one plus v times the derivative of the other. Then the quotient rule, it looks a bit different maybe than what you're used to, but I promise you it's the same rule as the quotient rule that you've learned. And well, yeah, here's the chain rule, and we're going to look a little bit more, but what you see is that u is a function, so you have to take the derivative of f to u and then multiply with the derivative of u to x. So there's a product there of 2 derivatives. That's good to remember. And then there's an inverse rule, but really that inverse rule is a special case of the chain rule. But have a look at it. The derivative of x to y is 1 over the derivative of y to x. Might come in useful sometime. Okay, so these are the rules, and now the very, very last thing of this lecture today is an example. So the method I like to use for the chain rule is called the plate method. And well, the chain rule is all about having one function inside another function. So what's the inside function here? It's t squared minus 4t plus 9. And to figure out what's the sort of outside function, then you can put a little plate on top of that one and see, oh, what do I have left? So it's 1 over the square root of something. Okay, so that's useful. Then so now you know the outer function and you know the inner function. Of course, you don't walk around with plates with you all the time, little rectangular plates, but actually a finger does the job very well. So let me show you in what's next how to then use this in the chain rule. So we'll finish today with an example of how to use the chain rule in differentiation. I told you to use your finger, which doesn't work here. I'll have to use my whole hand.
to cover it up. And what you see then is that our function, big function, so to say, is 1 over the square root. So that's g of x is actually x to the power minus 1/2. So the derivative here would be minus 1/2 times x to the power minus 3 seconds. 3 seconds. So, all right, this is the idea of the whole thing. So I can, yeah, I really prefer to write this as 1/2 times 1 over x square root of x. It's much more beautiful. So that's what I'm going to do here for the derivative. It is, I need a lot of space here. 1 over, now we can put this minus 2, of course, we can say 1 minus and then the 2 here. And then here you go, you get t squared minus 4t plus 9 times the square root of t squared minus 4t plus. And then the main thing of the chain rule is, of course, to then our hand was on top of this. We have to put the derivative of this there. So that's 2 times 2t minus 4. Minus 4. And don't forget it's there. Now that I've seen how big this is, maybe it would have been better to keep on using this notation. Anyway, there's no rule that you have to write it like this. So again, fine to also write minus 1/2 times t squared minus 4t plus 9 to the power minus 3 seconds times 2t minus 4. This is fine. All right, that's it. I wish you success with the quiz in a moment, and I'll see you in person if everything is all right next week. Good luck.